Okay, welcome everyone. I'm Diana Marculescu. I'm a professor and chair at UT Austin in electrical and computer engineering. And together with my colleague, George Papas, we put together this great panel. We have a distinguished panel here for you. The first half on data science and AI will just be short presentations from each of our panelists. So let me introduce each and one of them. We have Jelena Kovacevic. Jelena is currently the William R. Berkeley Professor and Dean of the NYU Tandon School of Engineering. And it was great to actually work with Jelena for many years at Carnegie Mellon when we were both there. So it's great to see her. We also have Rich Baranyuk. He is the Victor E. Cameron Professor of Electrical and Computer Engineering at Rice University. He is a member of the DSP and Machine Learning Research Groups and founder director of OpenStax. Welcome, Rich. We also have Asu Ozdalar. She is the MathWorks Professor of Electrical Engineering and Computer Science and the department head of the Electrical Engineering and Computer Science at MIT, also Deputy Dean of Academics of the Schwarzman College of Computing. And last but definitely not least, our last panelist is Stephen Boyd, is the Samsung Professor of Engineering, Professor of Electrical Engineering in Information Systems Laboratory, and Chair of the Electrical Engineering Department at Stanford University. So without further ado, I would like to have our panelists present their short 10 to 12 minutes. So Jelena, we can start with you.
Thank you very much, Diana. Good afternoon, morning, evening, wherever you are. Hi to my fellow panelists. I'm really excited to see you all and to be here at ECEDHA. I can tell you I miss being a department head. Some of my best times had been at ECEDHA. I don't really have the slides, but just a few thoughts and really not formally presented. And just at the outset, I want to apologize that I'll have to leave at 12:45 because I have my board meeting then. I think we all agree that AI is at an inflection point now. Technology is clearly advancing rapidly, and the need for AI or the wish for, thinking that there is a black box out there that can, solve many problems is happening in numerous fields. And we see major advances in techniques, in computer vision, in unsupervised learning, the enormous amount of unstructured data that's being collected every day. In 2018, according to a study by Sapient, and assuming that the amount of data generated double every day, it turns out that by this year or even previous year, the unstructured data will exceed all the data that exists today. So how does one prepare for this deluge of data, and how can we define, organize, understand it, manage it, and use this to advance societal problems, if you want? And one may want to look at the internet for a rough analogy where AI is headed as force in science and industry. As we all know, the World Wide Web began as ARPANET, a collaborative government and academic research cooperative that just 40 plus years ago involved around 40 nodes and just some rudimentary file transfer protocols. And today, of course, the internet is a globally distributed network of networks. It's the neurological system of our collective consciousness with as much storage capacity as the human brain, approaching some, 30 billion connected devices and 40 billion nodes. So kind of 40 to 40 billion in just 40 plus years. There could be some numerical mysticism involving the number 4 and what it all means, but it just tells us what an expansive growth this has been, and kind of perhaps shows us some sort of a template for the future of AI. If one thinks about where we are towards AI with human intelligence, there's a lot of, disagreement. Some say we're about 1% there, some say a little more. But collaborations between industry and institutions are driving use cases far beyond experimental applications. And there has been explosive growth in its use in research, products, service, medicine, our daily lives. And then, of course, in workplace, the research firm Forrester predicts that AI will impact 25% of all jobs in some fashion. My guess is that this is an understatement. It really depends how you count it. And then a Forbes article noted that machine learning algorithms, applications, and platforms are already improving semiconductor manufacturing yield by 30%, reducing supply chain forecasting errors by 50%, lost sales by 65%, and so on and so forth. But this, of course, not taking into account that we've been all in grips of a global pandemic. The interesting thing is, of course, that at the government level, there are a number of initiatives that might actually bring some resources towards this. There is that last week, for example, the Senate overwhelmingly passed a bill to bolster competitiveness with China. And that will allow for deeper research and funding, in areas such wireless, cyber, but of course, foremost among them, AI, data science, and robotics. Keynote, of course, is that this is not an appropriations bill, so the money is not flowing just yet. But, and of course, there is some anti-China language that we as academics are not on board with, but it may get worked out. So in some sense, there is an understanding that if we want to continue to thrive and if this country wants to lead, more resources need to be put into this. And I just want to address a few questions that were sent our way ahead of the panel about, for example, challenges and opportunities. Challenges, of course, are vast. I think I would single out healthcare, security, say securing the energy grid, anything to do with the urban environments, transportation, EVs, as we just heard, traffic monitoring, urban environment for elderly and disabled. But I think one of the biggest challenges, and this was somewhat touched upon in this just previous session, is what people are referring to ethical or responsible AI. The fact that social inequity is reinforced by data-intensive systems is not new. And advancements in data science and AI can be undermined by similar problems. Automated decisions based on biased data operationalize, entrench, and legitimize new forms of discrimination. And so as a result, there is really a need to build a shared and nuanced understanding of those issues and to chart a path towards solutions in which technical advances are combined with a shift in business practices and with the establishment of much needed regulatory mechanisms informed by public participation. In fact, in my school at NYU Tandon School of Engineering, we have a Center for Responsible AI. They catalyze policy and industry impact. They foster interdisciplinary research and education, and are trying to work towards building an equitable and socially sustainable ecosystem of AI innovation. And more, the local governments are thinking about requiring certain assurances of, let's say, algorithms that companies use. And so who will be that arbiter for deciding whether, yes, this piece of software or this product that you have is unbiased? Well, that can be us, right? And so what is the role in ECE in this emerging area? And then I will stop there and give it over to my colleagues. And so what research directions should ECE lead? As when I was a department head, I think the key is not pigeonholing ourselves into a niche that's too small, but rather expanding. Instead of saying, for example, robotics belongs to mechanical engineering, we say robotics belongs to ECE and we will collaborate with all disciplines to make it work. So, just instead of trying to find the niches that are purely EC, just be expansive, sort of total world domination if you want. I mean, in some sense, learning from computer science is without fear getting into all areas that we in EC might consider from before as being rightfully ours, but there is no such thing as being able to own an area. So I say, we just go out there and in some sense own them all. So again, on this note of total world domination by EC, I will stop. Thank you very much. And it's really wonderful to be here. I miss ECEDHA.
Thank you, Yelena. Let's move on to Rich.
Hi, can you hear me okay?
Sure.
Good, and I'll try screen sharing. Can everybody see my blank slide?
Yes, we can.
Okay, well, it's great to be here. Great to be with some old friends. And I think I'll also try to be brief, and I think there'll be a lot of resonance with what Yelena just said, which is great. And so I'm just going to make some quick remarks as we dive off this deep end into data science, artificial intelligence. And I think that at least to me, the overarching theme of the discussion today is really about cycles and remembering that ECE was born in a golden age of physics and physics-based models. And we're entering, as Yelena very cogently put it, a golden age of data and an age of big data. And really the future of ECE, I think, depends on how we navigate these waves. And if we're thinking about the future of ECE, I think it's maybe worthwhile to look at the past. So let's go way back. How far? I don't know. Let's go back 1,500 years or so to Babylon, right? And think about Babylonian mathematics and engineering. So the Babylonians were totally obsessed with data and calculating. So they figured out basically polynomial splines. In fact, they knew all the key theorems of the day. They were using them to predict things like eclipses and other astronomical events to really quite amazing precision, like 10% accuracy. And they were so obsessed with data that even the way that they taught students mathematics was different than we think about in the modern world. Basically, what they did was they had students work out large number of problems until they understood the general concept. And this will come back, I think, later, maybe when we talk about curriculum. But because of this total fixation on data, they were incapable of scaffolding any of these ideas together to create something larger. So let's move forward, fast forward a few hundred years to the Greeks. And the Greeks, as you probably know, were obsessed with models, right? The crazier the model, the better. For example, their crazy model of why the stars rotate in the sky was that between the great fire that burns eternally in the earth, there was a giant colander, right? Poked with holes. And this colander happened to rotate at a certain rate, and that's why the cosmos rotated. Now, this is a completely crazy model, but it's an incredibly useful model because it enabled Eratosthenes to use this model to basically calculate the circumference of the Earth, right? Again, interestingly, within about 10%. And so what we've seen is, and this is really the world where I would argue ECE has grown up in, is this obsession with physics, this obsession with building simple models that explain a situation and then building that can be analyzed theoretically, and then we can build powerful algorithms off of. Okay, but we're moving into this data-driven age, and I would argue that it's probably just about time that we are, because at least in my space, and Yelena lives in the same world of signal processing, so many of the really easy problems have actually been solved using this Greek approach. Here's a laundry list of methods solved over the last decades. And what's left are the really hard problems, right? Problems like object recognition, really accurate face recognition, speech recognition, robotic navigation. And these have really resisted this physics-based simple model-driven approach, but have yielded to moving from a physics math-driven modeling approach to really just throwing caution to the wind and embracing general purpose algorithms and architectures. The method du jour being deep learning, which has become literally a juggernaut, right? Just solving some very, very difficult problems, far exceeding the state of the art of the current way of doing things, and really opening the doors to some really interesting really interesting directions, right? And so this is the world that I believe we need to be navigating. And as Elena also alluded to, it's not clear to me exactly why ECE isn't getting the respect that it requires. Maybe it is that we're too tentative because of the long-term focus on well-grounded theoretical physics-based models and not data. But there's just no question that what we do in ECE is just totally central to this whole enterprise, from data science to AI. Like computer engineering literally is the infrastructure on which everything relies, right? And numerous other fields are being, either, I would say, less reinvented and often more rebranded, right, in terms of data science type lingo. And I think that ECE folks have a really important role to play, because just as computer scientists tend to have less fear, they're also less interested in actually studying the theoretical foundations of methods like deep learning, whereas ECE people, I think, are both better equipped and more likely to jump in and make important contributions. And I completely agree with Elena that we need to stop thinking of this space as somehow owned by statistics or computer science, but really looking at how we can collaborate with these other departments in order to move forward. So just quickly to cover the last couple points, or the questions that were asked by the panel moderators. I think the thing that is really probably clear to everybody, that this data science machine learning viewpoint completely inverts the traditional ECE curriculum. Instead of starting with math and physics and moving towards applications, maybe in a capstone project, we need to be bringing the data and applications in like immediately, right? And this requires that we move courses that are often taken later in our curriculum sequences much earlier. Things like linear algebra, statistics need to be moved earlier. But I'd really like to resist the urge to just, to give up on more mathematical or theoretical courses, because I think that's really a place where ECE really has a lot to give. Lastly, I think that it's pretty obvious that in addition to embracing curricular reform and hiring new kinds of faculty into our departments, and forging the kind of collaborations that that Elena talked about, I think it's really important as we move forward that we think carefully about avoiding unintended consequences. And I won't talk about this too much, but I'll just mention, as a person who works in this space, I basically live on this hamster wheel with these 3 big conferences that are spaced conveniently 4 months apart through the year, that have literally tens of thousands of submissions to some of these meetings, highly oversubscribed, low acceptance rates, as a result, very, very poor quality reviews. And computer science, I believe, made potentially a mistake about 20 plus years ago by locking their tenure process in with these conferences, with these highly selective, high perceived conferences. And it's created tremendous stress for a lot of young faculty in this space. And so, I just throw this out as an unintended consequence of what they thought would help their faculty, move more quickly than the journal publication process. So that's just one thing that I think folks might want to think about. And with that, I'll end and say thanks again for the invite.
Thank you, Rich. Aso.
Hello, it's great to be here with everyone. Let me also try to share my screen. Hopefully this will work. I always worry about Zoom and what it might do to me. Okay, wonderful. So I have a couple slides. I guess I will repeat many of the things that were said. I will talk about basically the promise and perils of data-driven decision-making, unintended consequences, focusing on the unintended consequences aspect, but different from Richard. I will basically focus on some societal unintended consequences that have been repeated multiple times in Emilio's talks, the Elena's, but I think one that we should be very cognizant of and embrace as ECE community. So let me start with, I guess, quickly with, promise success stories. Of course, AI and machine, I'm calling all of this data-driven approaches, but of course it sort of goes under AI and machine learning methods. These hold great promise in a number of applications. This was driven very much by, as Richard mentioned, the deep learning success stories, they've become extremely popular because of the breakthroughs they've achieved in a number of tasks in artificial intelligence, predominantly vision tasks. This is just sort of the example, I guess, that attracted all the attention to this area. This is the ImageNet, a large-scale visual recognition challenge, and the introduction of the deep learning methods or algorithms reduced the top 5 error by 10% in 2012. And over the years, deep learning models have dominated the challenges over and over. In 2015, people have trained very deep networks, 20, 30 layer networks that actually surpassed human performance. And this was, of course, created a lot of attention, a lot of excitement, use of these methodology in a number of immediate applications, thinking about image recognition, speech processing, and games, right? So AlphaGo was a big success by DeepMind. So moving beyond these sort of specific tasks of vision or games, of course, there's success stories also in specific AI systems. These range from self-driving cars. We already heard about that. There's a lot of success or promise held in medical diagnostics, and this is an example of another place where machine learning is creating a lot of excitement in other disciplines, scientific discovery. This is the so-called new antibiotic, halicin, discovered by the an MIT team. It sort of is a success story because it basically discovered a new powerful antibiotic that can kill many species of antibiotic resistant bacteria. And these are specific AI systems. I also want to sort of draw our attention to many very largely AI driven, data driven, large scale systems. These are smart infrastructure systems, or you can think about them as other names that are used are socio-technical systems. This ranges from energy power systems to mobility to healthcare delivery. So success stories are everywhere. And what are the challenges? What are the opportunities maybe for EC, for people with our background in design of these systems? Of course, the most common goal is performance. We are trying very hard to make sure we get accuracy, performance, to be able to add positive value. But of course, accuracy or performance are not the only metrics. Robustness issues, thinking about making sure these systems can be used with unvetted, trusted data. They can be robust to perturbations in input data or domain shifts or any changes in the environment used for training these systems. Reliability, sort of, we need to make sure these can degrade gracefully, even in the presence of misspecified, unspecified models. And these are extremely important, of course, whenever we think about safety critical applications. And the other sort of big opportunity for ECE folks, or in general, is the fact that these systems are embedded very much in physical infrastructures. They use real-time data. This is very much sort of a big community that's emerging, in which George is very involved with, the sort of learning for dynamics and control, L4DC. So sort of very much, I guess, motivates us to move beyond just pattern recognition, supervised learning, classification type problems into data-driven control and optimization of dynamical systems. So there's a lot of excitement, a lot of research activity going on in these areas and topics. Many of the students are crazy about working on these. But also, when you think about, issues and challenges, we're really, seeing the tip of the iceberg yet, because if you're thinking about really real-world deployment of these systems in the society, in the presence of humans, you start sort of running into a lot of issues. So, this is self-driving cars crashing into buses. The other one, which is sort of very much in the news, is the bias introduced by these sort of tools that are used for various decision-making tasks. Another one that sort of is very much, keeping the public very busy is the effect of these platforms, AI-driven platforms, and how it's changing our fabric of our society. For instance, social media is an important example here. It was considered as a fundamentally democratizing technology that would bring people closer together, expose them to diverse opinions. However, it turned to be further ground for spread of fake news, leading to polarization. All of these exacerbated by the content recommendation algorithms, very much driven by AI models and algorithms, or filter bubble algorithms. Also, a lot of stress around work of the future, how automation and development or incorporation of these intelligent systems into our workforce affects the welfare, equities, and very much the standard of life of all of our society. So I think in terms of the challenges, I would like to very much focus on this particular aspect. So these are, very much I mean, I think many people have already talked about this. Yelena talked about, responsible, ethical deployment of these systems. I'd like to just, I think both bring out this aspect of human factors. I view this both as a very important challenge, but also a great opportunity for us to embrace in terms of expanding our boundaries and, taking a very holistic view on how these systems can be developed, deployed, and used. It's the foremost the recognition that these are technologies that have to work with and for human actors. And I think there's been relatively little attention paid to how this interface takes place, how they can be misused by people, and how in turn they can change human behavior. And I very much feel this is sort of an important place where, we can make it impact, because these are very much about feedback effects. These systems work with, they impact human behavior and work with data that is coming from humans, and lead to unintended consequences that, one needs to take into account while thinking about addressing how to deploy these systems. So I'd like to highlight two main challenges. Already these have been mentioned partly. One is very much the socially responsible deployment of AI. Clearly, this data-driven decision-making is permeating every aspect of our lives. A primary example is criminal justice, but also these kind of, in criminal justice all around the country, judges or parole officers are very much using algorithms to be able to decide whether a criminal defendant is likely to, become a recidivist, a term used to describe criminals who will reoffend. And this is not the only place these algorithmic decision-making tools are used. They're used basically to decide who, based on online personality tests, who is the right person for the job. The credit scoring, algorithms play an enormous role on who gets a mortgage, who gets a credit card, or even, in the most mundane things, such as, who gets the best cell phone deal. And it's, I think, critical in designing these algorithms for us to think about, how these technologies should be deployed, developed, so that they don't create undue burden on some groups, especially those suffering disadvantages. This is sort of a very stark example, a story that was a study actually that was done by ProPublica, which is a nonprofit news organization who analyzed the risk assessment tool Compass used by, in the criminal justice system to determine the risk score for criminals to reoffend. And what this is sort of, I guess you can read it from here. There's software used across the country to predict future criminals, and it's biased. This is cut against blacks. So these are issues that we all should be cognizant of, I think, in trying to think about our work. The second one is also, I would like to point out, is human technology interactions. And as I mentioned, technologies are not just used by humans, they also change human behavior, reasoning, and preferences. And AI is an important factor that actually multiplies all of these capabilities. So if you think about, content recommendation systems, online platforms, how they change our behavior, our way of life, basically, there's a huge amount of personal data that is generated and used by these platforms to be able to do personalized recommendations, targeted ads, changing completely the way humans behave, learning about our preferences even better than ourselves. So there's this question of who controls, regulates how these technologies will impact humans. I already talked about, social media and issues around that, recommendation algorithms, which is very much at the core of many of the, work done within statistics or EC is very much also at the core of this. So I think it's very important to understand how these AI-powered algorithms can be deployed, how they change human information, and how we can actually take into account these feedback effects in designing these systems. So there's a lot of excitement, I think, around all these questions, a lot of things that we can contribute in sort of making a societal impact in design of these systems. And I just want to say a little bit about the role of EC, as well as, I was also asked to talk about educational curriculum reforms, and we are doing a lot at MIT to address these issues. I strongly believe that many of the problems that I've talked about very much require combining data-driven decision-making, AI, ML, but also this sort of systems viewpoint. Control, optimization, game theory, dynamical systems analysis, and also, coupled with social science modeling and perspectives. I think this is a place where ECE can lead, can make great impact, because it's the one discipline which has, I think, all of these components embedded in it. And at MIT, we recently reorganized the very big ECS department to actually be able to capture this burgeoning area. ECS is a large department. It was always considered as two units, EE and CS. I think over the past couple of years, it has become clear to us that that doesn't seem to be the right division in thinking about, departmental functions and activities, research activities. So we decided about a year and a half ago to reorganize it into 3 units. This new unit is called AI and decision making, and we basically envision it to bring together CS heritage, AI and machine learning with EE heritage, information and decision systems, to actually, highlight a set of people working on similar problems with similar methodologies and interests. And we have been working very hard with a group of faculty over the past year and a half to define this new discipline and to design a new major around it. Very quickly, this is our current definition of AID. It develops techniques for analysis and synthesis of systems that interact with an external world via perception, communication, and action. It integrates disciplines typically taught in different departments, including EE, CS, statistics, and operations research under one umbrella. So this seems to be working very well in terms of all the new educational innovations, research activities that are ongoing in the department. And I just wanted to end by a quick, highlight of a brand new AID major that we are designing. We're hoping to launch this next year. This is supposed to be an eye chart. It's still under development, so I didn't want to, share all the details. But the excitement, I think, is the fact that we are designing a new core fundamentals that Richard, I think, alluded to much of it in the context of ECE, that actually says we don't just need discrete, we don't just need continuous, but also discrete. We need to combine discrete and continuous algorithms so our students can actually understand, seamlessly interface between the two. We need to develop discrete continuous math foundations, definitely early on probability and statistical inference, linear algebra and optimization, a lot of programming, but much more for data science than how it's taught in CS. And then also some core that actually combines different sets of classes that we're developing, which are supposed to be data-centric, model-centric, computation-centric, and decision-centric, and leading to several different application areas, which uses this core at its foundation and develops these exciting new opportunities for our students. So with that, I will, I guess, stop and just say that I think there's a lot of excitement around these areas in ECE, and this is sort of leading to a lot of different organizational changes in the structure of the department. So it's a great, exciting time to embrace these opportunities and challenges moving forward.
Thank you, Asu. Stephen.
Hi. Well, first of all, I should say that I agree very much with everything that Jelena, Asu, and Rich said. I also didn't prepare any slides, and actually I'll just say a few things. So first, one of the questions we were asked to think about is what role will ECE play in this coming, data science, AI, ML, and the answer, I think, is pretty clear. It's going to play a role, but the important part is that many departments will. So will statistics. So will computer science. If you're at a school with a separate computer science department. Now, it's interesting because that makes actually a bunch of my colleagues actually quite uncomfortable. I think several people have already referred to that, and in fact, I even had one of my I guess we refer to him. He actually self-identifies as an EE nativist, and he actually said, oh my God, when we did networking and stuff like that, we owned it. Like, what can we own now? Anyway, I disagree vehemently with that. I think it's actually very destructive. Those are very destructive ideas. So the point is actually ECE has done this before. I mean, this is very much like control. Control is not owned by ECE. That's ridiculous. It depends on the university. It's done by mechanical engineering. It's done by Aero Astro. If you have such departments, it can be done by a lot of departments. You have people in computer, in computer science sometimes doing control, and that seems to have worked out very well, where it is in fact not owned by any one department, but in fact what happens is the departments have different dialects they speak, and I think that's actually very powerful for the students to go from one place to another and actually hear different dialects, to talking about the same material. So this has also happened, of course, with devices, right? Where, I mean, device people they could be in applied physics, they could be in material science. And again, I think as long as, we commit to low boundaries between departments, and certainly not rigid departments, rigid identity tests or whatever, I think this is actually a really good, I think we'll be able to contribute, not own data science, AI, and machine learning. So, or in other words, I would advocate for big tent ECE. So that's what I would advocate for. I'll say just a little bit about educational reforms, because we were asked to say what does all this mean about what do we teach? Well, the first thing is kind of obvious, is we can't keep teaching the same 1960s signal and image processing, right? And any more than in a control curriculum, you can keep teaching root locus, Bodie plots, lead lag controllers, and ignore more modern methods like MPC, not even to mention things like reinforcement learning. So I think the key for us, the key challenge is actually to blend the classical with the new AI and machine learning ideas. I think Rich, I think several people have, Asu referred to this, Rich referred to it. And I think that's the idea, is to blend these two. Now, by the way, that's not gonna be done by simply randomly removing 30% of the topics in the existing course that traces back to 1960s. It's actually going to take serious intellectual triage. And what I mean by that is you go back, we took these courses when we were getting our degrees. And yeah, I mean, you have to look at each topic and figure out, really, that was wonderful. I enjoyed it. It's awesome material. But seriously, do we have to, does that need to be there? And so that's serious work. And I think a lot of people don't think of it that way. They think of it as simply going through and doing, I guess what they call, there's a great euphemism, when you're building a building and it costs too much, they do value engineering. And that means they remove things that are too expensive one by one. This is not that. Okay, so I think actually that if we do this right, if we actually blend the cultural background that we bring to the problems, which I think Rich talked about very well, so did Asu, that these are which is using math and mathematical things to actually solve practical problems. I think if we bring this kind of culture to the table here, I think it's going to be very powerful. So we have a lot to offer, right? So we've been doing signal processing, filtering, signal detection and control for a long time. I should also add, now I sound maybe a little bit like my colleague, but we know physics. And to be honest, that's not something you can say about the typical CS or statistics, ML, and AI student. So I remember meeting a couple I also have students in computer science, absolutely brilliant. And I remember we were talking about something, and what I quickly figured out was actually he didn't know about differential equations. I mean, just basically differential equations. Like I was writing them on the board, and he's like, what is that? So it was interesting. Anyway, I feel that if we do this right, it's going to be awesome and powerful. It'll attract students from CS and STAT, and that's just fantastic. I just want to finish to mention one thing that I am actually rather worried about, and it's not a big picture thing like other people have talked about, and I'm glad they did, because I guess I don't have to. But one specific thing I'm actually quite worried about. It's the education of some students in data science, AI, and machine learning. And what's happening is a lot of people are simply learning, the quote learning, whatever that means in this case. It's not entirely clear to me. As Rich put it, the algorithm du jour, right? So, I mean, it's just stunning to me that I actually see people leaving with all kinds of degrees, BS, MS, PhD, who can tell you everything about what happened at NeurIPS last year or something like that. But they basically just, accidentally forgot to learn the basics. And that's it's weird. So I've seen it's also very bad, and my suspicion is that there'll be a backlash. I think it's already coming, and that sort of thing. So I think that's something where I think we would play a very important role to make sure that students do know the basic statistics, the linear algebra, the optimization. Do they have to know as much as when these things were the only thing to know? No. And I think what that requires of us is to create what are called outreach courses. So an outreach course is one where it's not targeted at the experts, the 14 students in your PhD program studying that, or at the undergraduate level. It's not meant just for the students who have chosen that subspecialty. It's actually meant for sort of everyone in EE, everyone in CS, everyone in statistics, and things like that. I think we can construct these courses. We've done some of that at Stanford. It's been a lot of fun, and I think it's been good. Okay, so I think what I'll do is I'll quit here, and we'll head on to the next panelist.
Thank you, Rich. Sorry, thank you, Stephen. I was You mentioned Rich, so this is why I brought him up again. So
I agree with everything Rich said, so that's fine.
I know. Unfortunately, we lost Yelena, and we do have a few minutes before we hand it over to our corporate speaker. But I wanted to bring up a question that all of you have mentioned, from world domination of ECE to creating new majors to outreach to other disciplines or other programs. So is there a recipe that we should follow, or just depending on the strengths of each program or each institution, I guess we should try to do on our own, or identify what works best for each? And I think I know the answer, but I thought I would throw it out there.
Well, if no one else will respond, I will.
Yeah, cool.
Yes.
Yeah, I think it should be done dependent on the local culture. Local culture actually, it makes a big difference. And so, if you have a combined E&CS department, that's one thing. Or if you have a separate statistics department, that's another thing. If you don't have a statistics department, Asu, that would be you. Then that's a different thing.
We have a center.
I know that. I know. So I think it should actually be done locally. Also, I think that this idea of creating this new curriculum, and of course I think it's the same at the graduate level and undergraduate level. It's actually really hard. It's not at all clear that this is something that junior faculty should. I mean, if they want to do this, this is absolutely wonderful. But it's not at all clear to me that they should be doing this kind of thing. That it actually requires people who've been doing this for quite a while to actually do the triage stuff.
Right. There's a twist on I don't know if you're seeing the chat, but there's a twist on the question from the audience. How do we explore some of these ideas to smaller institutions? So I'm sorry, I cut you off.
No, I just wanted to sort of add on to Stephen. Indeed, we don't ask junior faculty to do this, but what happened with us in the AID major is actually they were very interested in stepping and they taught this sort of division between E and CS. This belongs to E, this belongs to CS, does not make much sense anymore. So they wanted to actually step up and say, we would like to start from what we're excited working on. And then from there, we would like to develop some fundamentals. So that curriculum committee that I just mentioned, 20 people, actually did include several junior faculty who were very excited about developing these courses that could be the new fundamental for these applications that they're interested in. And also they're very interested in this sort of responsible, ethical use of AI. So there's also a number of classes they are interested in developing around AI and society. But I just want to also maybe address this question in the chat, but also, your previous question, Diana, about what's the recipe, how do we do this in smaller institutions? I totally agree with Stephen. It's what changes you're going to implement and the form you're going to implement it in very much depends on the structure of your department, how it connects to other places across the institute. But what we are finding at MIT is also a great opportunity, and I'm sure this is happening elsewhere also, to connect with other departments and create actually these cross-cutting initiatives between departments. So whether this is, we have a new initiative in the School of Engineering called NEAT, sort of educational transformation. So it has these tracks around climate or sustainability or robotics or living machines that are actually very much drawing from several disciplines, involves collaborating across different departments to create these very rich educational experiences for the students. So I'm very much I think I don't know, remember who said that, to bring the boundaries down, departmentless. I mean, departmentless is, I think, probably difficult. I don't know how to run such an institution, but very low boundaries in which people work with each other. On the educational reforms, try to collaborate and create these offerings in collaboration. For instance, just as an example, Stephen would relate to this very much. We recently developed a new course. These are two of my colleagues, Pablo Parillo and Ankor Moitra, a new linear algebra class. And then their point was very much following several offerings that Stephen was involved in. Linear algebra should not just be taught as a math class with recipe-driven approaches, but it should be much more computational, much more geometric, much more related to data science applications. So how can we actually create such a new class? They did that. They did this beautiful class last term. Now it's actually became the substitute for linear algebra across MIT in many, many departments. So I think these things are happening. There are a lot of changes that we should embrace. I'm totally very excited because the knowledge of physics, differential equations, as well as systems viewpoint, and now with these new modern approaches, I think promise great impact moving forward and a great way of changing all disciplines across our institutions. So I hope Steve will agree with me.
I do. Actually, I just wanted to very quickly respond quite directly to Miguel's question about how do we export some of these ideas to the smaller institutions. So actually, I think there's a wonderful thing right now, and that is that a lot of these courses that people are developing, these interesting radical new courses and things like that, almost all of them are entirely online. And so it's awesome. I mean, you get to poke around and see what people at Berkeley are doing in Data 8. Right? And you might agree with some of it or not agree with some of it, but I think it's really good, I think, for us to be able to do that. And I think that's actually, so what that means is that at a smaller institution, you can poke around and find out what Rich is up to, what Asu is up to, what George is up to. And I mean, it's great. You can pick and choose and stuff like that. And I think actually that's an important culture for us to embrace, right? Well, Rich has been at the forefront of this for a long time. This idea that the stuff we do, we should make available to the entire world. So has Magnus, right? And I just think, and by the way, it doesn't have to be that way, right? If I look at my colleagues in the business school, everything is locked down. They charge each other for you have to pay like Harvard Business School for cases, whereas I think we have a much better culture, which is we just put everything online, and you want all the code is on GitHub, done. So
thank you. We will come back to the discussion, but we need to introduce our corporate speakers. So I'm going to hand it over to Chad Alley from MathWorks.
Hi, yes, thank you, Diana. I appreciate it. So hi, everyone. My name is Chad Alley from MathWorks. Today, we're going to be having a corporate suite to discuss a little bit more about AI, some of the themes we touched on, such as systems design and bias in data and things like that. And so we're going to be talking about different workflows, examples, and use cases in real life, and then how we can get started in different curriculums.
Thank you, Chad. And we will resume our discussion at 20 after 12, so 12:20 Central, 1:20 Eastern. And I believe there was a message, the corporate suite will open soon.
Yes.
Thank you. Thanks.
Actually, I was confused by the message. Megan, are we all being moved back into the main room first and then we take it from there, or?
Yeah, so this is Michelle. The breakout rooms will close in 5 minutes. Everyone will be back in the main room.
Cool. So we have 5 more minutes.
Yes.
Then maybe we can have Rich finalize the discussion we had.
Me?
Yes.
Oh,
because everyone got to chime in on that.
Like a wrap. Oh, around. Yeah. So I think
on how we translate some of these ideas to smaller institutions, or perhaps
is one of those
the recipe.
Right? Yeah. And so I totally agree with this idea of we're in such a lucky place today, unlike say 40 years ago, where it's literally possible to see what other schools are teaching. So it makes like the experimental space of institutions now is, there's like 100 schools that are experimenting with different ways of teaching data science, AI type ideas. And so we can learn from a lot of these materials that have been put online. I think going back to Elena's point, I think the importance of collaborating with other departments in your institution, for example, statistics and computer science, I think only becomes more critical when you're in a small school. So when you're in a huge EECS department with 100 plus faculty, you probably have critical mass of folks. But if you're in a smaller place with say 20 to 30 EE or ECE faculty, then it's just critical to build those bridges so that you can teach the kind of courses that you need to teach. So I think there's no question that it's just a really exciting time. And so much of ECE was kind of locked down in the 1960s, 50s and 60s with the publication of some of the key textbooks and setting of the curricula. And I think it's going to be really neat to look back in 10 years from now at how much our curriculum is probably going to change over this next decade. So it's, yeah, like Stephen said, it's a very exciting time.
Thank you, Rich. And just a clarification, we're going to break whenever we get disconnected, we're going to break to the main room for the corporate suites, but we are going to be back for discussion at 12:20 Central, 1:20 Eastern.